Hello everyone, I am Lavanya, Assistant Professor in Department of Computer Science and Engineering Department at Sri Venkateshwara College of Engineering. So today we are going to see Unit 4 network in network and networks with parallel concatenation in Unit 4. So let's get started. So network in network or NIN. So in a standard convolutional neural network, convolutional layers use linear filters to scan the input, followed by a simple activation function like ReLU. So these filters capture basic patterns such as edges and textures, but their operations are fundamentally linear. NIN takes this idea further by embedding micro neural networks, specifically small fully connected networks called MLP convolution layers inside the convolutional layer. So instead of applying a single linear filter at each spatial location, NIN applies a tiny multi-layer perceptron to learn more complex non-linear transformation. Why use this approach? So traditional CNN filters are limited to linear operations plus activation, which can restrict the model's ability to capture highly abstract patterns. NIN's MLP convolutional layers introduce non-linearity inside the convolution itself, enabling the network to learn richer, more complex features without simply increasing the size of the filters. This makes NIN especially powerful for tasks that require recognizing subtle patterns or high level abstractions in data. So all in this while keeping the model computationally effective. So NIN replaces simple linear filters with small neural networks, allowing deeper feature learning and better pattern recognition in images. NIN block structure and how it works. Unlike a traditional CNN block, which typically contains a single convolution layer, a NIN block is more sophisticated. Each block starts with a standard convolution layer to extract basic spatial features. This is followed by several one-by-one convolutional layers which act like tiny multi-layer perceptrons applied at each spatial location. After each layer, a ReLU activation introduces non-linearity, allowing the network to learn complex patterns. Between blocks, pooling layers are used to downsample the future maps and reduce computation. Now, how does NIN work in practice? At the end of the network, one-by-one convolution replaces traditional fully connected layers. These one-by-one convolutions perform per pixel MLP operations, which enhances feature abstraction locally across the spatial dimensions. This design enables the network to capture more intricate and expressive features without dramatically increasing the number of parameters. So NIN blocks allows the network to be deeper and more expressive, learning complex local patterns while remaining computationally efficient. It combines the spatial understanding of CNN with the nonlinear expressive power of small MLP. So NIN architecture overview. So it begins with an architecture similar to a AlexNet, especially in its earlier layers. It uses large convolutional kernels such as 11 by 11 in the first layer, followed by 5 by 5 and 3 by 3 kernels in the deep layers. These varying kernel sizes helps the network capture features at different levels. The larger kernels in the beginning help to extract broad, low-level features like edges and textures, while smaller kernels in deep layers focus on more detailed and complex patterns. The number of output channels in these convolution layers is also kept similar to AlexNet. This ensures that the network maintains a sufficient feature extraction capacity while still following a familiar architectural design. So let's focus on key innovations. The NAN block structure. Each block is not just a simple convolutional layer. It is a combination of a standard convolution layer followed by one convolution layers, also known as pointwise convolutions. The main purpose of these one by one convolution is to increase the level of non-linearity in the network without increasing spatial dimensions. They work across the channel dimension, allowing the model to learn complex relationship between feature maps. This improves the expressive power of the network while keeping the model lightweight. So as a result, NAN is able to learn richer future representations compared to traditional convolution architectures while still being more efficient in terms of parameters and computations. After each NAN block, a max pooling layer is applied. This layer typically uses a 3 by 3 window with a stride of 2. The main purpose of this operation is to progressively reduce the spatial dimension of the feature maps. By reducing the width and height of the feature map, the model becomes computationally more efficient. At the same time, max pooling helps in retaining the most important features while discarding less significant information. Another important role of pooling is to control overfitting. By reducing the number of activations, it limits the model's complexity and improves generalization on unseen data. Now moving to the key difference in NIN architecture. So traditional convolutional neural networks such as AlexNet and VGG, NIN completely eliminates fully connected layers. Fully connected layers usually require a very large number of parameters and consume significant memory. Instead, NIN introduces a more efficient approach. It uses a final NIN block where the number of output channels is equal to the number of target classes. This means that each channel directly corresponds to one class. After this, a global average pooling layer is applied. This layer takes the average of each feature map and converts it into single value, producing a final vector of class scores. So this approach preserves spatial information until the very end of the over network and drastically reduces the number of parameters. So overall, by combining efficient pooling and removing fully connected layers, NIN achieves a compact, memory efficient and effective deep learning model. After the final NIN block, we apply global average pooling. So this operation converts the feature maps into logics vector, which directly represents the class scores. The key benefit is that it provides a direct mapping from features to output classes without using fully connected layers. Coming to the advantage of NIN design, it significantly reduces the number of parameters, making the model more efficient, more memory efficient. It also maintains the spatial structure of the data and performs more efficiently compared to earlier models like AlexNet and VGG. This makes NIN a powerful and compact deep learning architecture. The main advantage of NAN is its lower memory usage since it removes the fully connected layers. However, the trade-off is that it may slightly increase the training time. NAN works by using convolution layers along with one by one convolutions to improve future learning. It replaces fully connected layers with global average pooling. So NIN becomes an efficient and compact deep learning model. Now let us analyze the training performance of the model. The blue line represents the training loss and we can see that it steadily decreases over the epochs. This indicates that the model is learning efficiently from the training data. The orange dashed lines shows the validation loss. Initially, it follows a similar decreasing trend, but around the middle epochs we observe a spike. So this may indicate a slight overfitting and instability during training. The green line represents validation accuracy. It consistently increases over time, which shows that the model is improving its performance on unseen data. Overall, the model demonstrates good learning behavior with decreasing loss and increasing accuracy, although minor fluctuations suggest the need for careful tuning. This concludes the analysis of the training graph. So the layer types and their roles in NIN architecture. First, the convolution layer, such as 5 by 5 convolution. This layer extracts the initial features from the input like edges, textures and basic pattern. Its output shape is typically H by W by C, where H and W are the spatial dimensions and C is the number of channels or feature maps. Next, the one by one convolution followed by ReLU. This layer performs a non-linear combination of features across at each spatial location, allowing the network to mix information across the channels. So the output shape is H by W by C, introducing more abstract features like keeping spatial dimensions the same. Then another one by one convolution and plus ReLU layer further abstracts the features, enabling the network to capture even higher level patterns. This output shape becomes H by W by C, adding depth in the future dimensions. Finally, the pooling layers perform spatial downsampling. This reduces the height and width of the feature maps, lowering computational cost and focusing on the most important information. After pooling, the output shape is smaller in H and W, while the number of channels remains the same. So NAN layers combine standard convolution for feature extraction with the one by one convolutions for local feature abstractions and pooling layers for efficient downsampling, resulting in a compact yet powerful architecture. Advantages of network in network. First, it provides a better local feature abstraction compared to simple convolution layers, capturing more complex patterns in the data. Second, it uses a smaller number of parameters than fully connected layers, making the model more efficient. And third one, NIN acts as a learnable nonlinear filter, not just a linear one, allowing the network to extract a richer representation. Finally, it helps to improve classification accuracy while keeping the number of parameters low, making it both powerful and efficient. Networks with parallel connections, concatenations. So it processes the input through multiple parallel paths or branches at the same time. Each branch applies different types of operations such as filters of varying sizes to extract unique features. After processing, the outputs from all branches are concatenated depthwise along the channels. This design allows the network to capture diverse features across multiple scales or aspects, improving its ability to understand complex patterns. So, why use parallel concatenation in neural network? First, different filter sizes capture different spatial features from small edges to large textures. Second, combining multiple branches helps to build richer feature representations by providing multiple perspectives on the same input. Third, it improves the model's ability to understand complex patterns in the data. So finally, this approach is used to extensively in architecture like inception networks, also known as GoogleNet, and in some dense net. To start with standard convolutions such as 5 by 5 filter, which extracts the initial feature from the input. So the output shape at this stage is height by width by the number of channels. So next we use one by one convolution followed by a ReLU activation to perform a non-linear combination of features, which producing an output with updated channel dimensions. Another one by one convolution with ReLU is applied to further abstract the future, again updating the channel count. Finally, a pooling layer performs a spatial downsampling, reducing the height and width of the feature map. So let's look at the parallel branches. Branch 1 applies a simple 1 by 1 convolution. Branch 2 uses 1 by 1 convolution followed by 3 by 3 convolution. Branch 3 applies 1 by 1 convolution followed by 5 by 5 convolution. And branch 4 performs 3 by 3 max pooling followed by 1 by 1 convolution. The outputs from all these branches are then concatenated depth-wise to form a rich and diverse future representation. Suppose we have three outputs from different branches x1, x2 and x3. To combine their information, we perform a depth-wise concatenation. Mathematically, this is expressed as y equals concatenate of concatenate of x1, x2 and x3. This operation joins the feature maps along the channel dimension, creating a single richer representation that captures all the diverse features from the block. So let's talk through the inception model through network example. We start with input of size 32 by 32 with 3 channels. The input is processed through 4 parallel branches. The first branch applies a 1 by 1 convolution producing 16 feature maps. The second branch uses 3 by 3 convolution producing 32 feature map, and third branch uses 5 by 5 convolution also producing 32 feature maps. The fourth branch performs max pooling followed by a 1 by 1 convolution producing 16 feature maps. After all branches have processed the input, their outputs are concatenated along the channel dimension. The final output is a combined feature map of size 32 by 32 with 96 channels, capturing diverse features from all the branches. Here is the structure of inception block. The inception block consists of 4 parallel paths that operate simultaneously on the same input. The first 3 paths use convolution layers with different window size such as 1 by 1, 3 by 3 and 5 by 5. These different kernel sizes help the network capture features at multiple spatial spaces. The middle paths include 1 by 1 convolutions which are used to reduce the number of channels before applying large convolutions. This significantly reduces the computational cost and makes the model more efficient. The fourth path applies a max pooling operation followed by a 1 by 1 convolution. The pooling layer helps in downsampling the spatial dimension, while the 1 by 1 convolution adjusts the number of output channels. All 4 paths use appropriate padding so that the input and output feature maps maintain the same height and width. So finally, the output from all 4 paths are concatenated along the channel dimension to form the final output of the inception block. The main hyperparameter that is tuned in the inception architecture is the number of output channels in each layer, which helps to balance performance and computational efficiency. This completes the explanation of the inception block. Types of parallel combination. When combining outputs from parallel branches in a network, there are several approaches. The most common method is concatenation, which merges the feature maps along with the channel dimension. Another approach is element-wise addition, which corresponds features from each branch are summed together. Finally, some networks use hybrid combinations which mix concatenation and addition to leverage the strength of both methods. So first, concatenation method or concatenation operation. It combines the feature maps along the depth or channel axis. This increases the richness of the features, allowing the network to capture more diverse information. It's widely used in modern architectures such as inception and densenet modules. So mathematically, if we have outputs f1 of x and f2 of x from two branches, the concatenated output is simply f of x equals the combination of f1 of x and f2 of x. This notation shows that the feature maps are joined channel wise into a single richer representation. So next, parallel convolution example. So the network applies filters of different sizes 1 by 1, 3 by 3 and 5 by 5 simultaneously to the same input. This allows the network to capture features at multiple scales from fine details to large patterns, creating a richer representation for downstream tasks. Networks with parallel concatenation offers several advantages. First, they can extract features at multiple scales and complexities simultaneously, capturing both fine details and large patterns. Second, they are more efficient than stacking many layers sequentially, reducing computational cost while maintaining performance. Third, by combining diverse feature sets, these networks help the model learn better representation and improve overall accuracy. Several other networks use this concept. For example, DenseNet employs dense connections, concatenating feature maps from all previous layers. Parallel concatenation is also widely used in multi-branch architectures in both NLP and vision models. By processing data through multiple branches simultaneously and then concatenating their outputs, network like Inception, also known as GoogleNet and DenseNet, build powerful representation that drive state-of-the-art performance.